Hi guys, in this lecture we're going to look at a couple of applications of differential equations. In particular, we're going to talk about growth and decay in a couple of different settings. The first setting that we're going to talk about is in the setting of continuous interest. And the second setting that we're going to talk about is Newton's law of heating and cooling. So let's first talk about continuous interest as an application of differential equations. So the idea is that at every instant, your account earns X percent of the current balance. You're accruing interest continuously. Now, this is something that I'm sure you've studied in pre-calc, but just as a quick review, you can earn interest quarterly if you put money in the bank. You can earn interest monthly. You can earn interest daily. And what's happening is when you break the year into a larger number of subintervals, you're taking the amount of interest that you earn per subinterval and you're dividing it by the number of subintervals. So you're earning less interest, but you're then compounding it more times per year. So that's actually better for you to do than compound it once. So for example, if you take 8% and you compound that once per year, it's actually better. So that would be 1.08 times whatever you had at the start of the year. It would be better for you to compound that twice a year. So what that would mean is you take 4%, which is half of that, and then square it. So the 1.04 times 1.04. With continuous interest, what we're doing is we're taking the limiting case of this. So what we're doing is we are taking the number of subintervals over the year and have it approach infinity. And you may remember from pre-calc that you get a formula P e to the RT or something like that. So we're going to derive that formula, but from a calculus perspective. So let's do that through an example. Let's say you earn 6% compounded continuously and start with $500. Use diffq, differential equations, to find the balance at time t. So we're going to start with the differential equation which models this, and we're then going to back into an actual equation for the balance. So let's see, the rate of change, dB dt, the rate of change of the balance at time t is, well, try to pause your video for a second, see if you can come up with that. Well, if I'm earning 6% compounded continuously, then dB dt, the rate of change, let's see, it earns X percent of the current balance. It's just going to be 0.06 of whatever I have at that point of time. So it'll be 0.06 times my balance at time t. Well, we now have a differential equation that we can solve using our separation of variables method. So I'm going to give you a minute, pause the video, try to solve it, and then you can see my video solution. Hopefully you see that this could be, for example, my function of t. This guy could be my function of b, so it is a legitimate separation of variables problem. Multiply, quote unquote, by dt, divide both sides by b, quote unquote, and then integrate. Balances are positive, so I'll have the natural log of b. I don't need the absolute value. And this guy is 0.06 t, again, plus c. We've played this game before. Let's exponentiate both sides. So we have that b is equal to e to the 0.06 t times e to the c using properties of exponents. So that b is a e to the 0.06 t. Well, we have this formula. B is some function of t. It's equal to some constant a times e to the 0.06 t. Can we solve for a? Yeah, we can, because we know that at time 0, we have $500. So b of 0 is 500, and that equals a e to the 0.06 times 0 is just 0. So it looks like a is 500. So b, or b of t, is 500 e to the 0.06 t. So there's my p e to the rt for those of you who remember this from pre-calculus. So that's one application. The second application that I'd like to investigate is Newton's law of heating and cooling. So Newton, who was one of the fathers of calculus, was a mathematician, a scientist. He did everything. And one thing he studied was heating and cooling as a part of thermodynamics. And let's see what he discovered. So this is Newton's law of heating and cooling. So experimentally, he discovered that if something were, sorry, this should be my starting temp. If an object were placed in a room, then if an object that were hotter than the current room temperature were placed in a room, then this graph would show us how the temperature decreased. So we're getting closer and closer to room temperature. So you might be putting a hot piece of pizza in your room as an example. So this would be a graphical representation of Newton's law of cooling. Graphical representation of Newton's law of heating might be where you put a slice of pizza that you haven't cooked yet, you put it in the oven, and it's heating up to the temperature of the oven. And he discovered, let's talk about this one. You can exchange it for this one pretty easily. But this one, he discovered that the temperature decreases at a rate proportional to the difference between the temperature of the object and the environment. So I know it's a mouthful. And again, decreases, I can exchange that for increases if I like. So let's read this. So the temperature decreases at a rate that's proportional to the difference between the temperature of the object and the environment. So what does that mean here? So decreases at a rate, so that's going to be some sort of derivative. What the heck does proportional mean? Well, proportional, if x and y are proportional, then that means mathematically that there's some constant k such that k times x equals y. So as an example, a real life example, let's say coffee costs you $3 a cup, then 3 over 1 would be if I have 1 cup, if I have 2 cups, 6 over 2, if I have 3 cups, 9 over 3. This ratio, my y over x, output over input, is a constant. So that's what it means to be proportional. So there's going to be some value k here to the difference between the temperature of the object and the environment. Okay, so difference I think we're all familiar with. So what I'd like to do is give an example now where we can see if we can use this language and convert it to a differential equation. So let's do an example with pizza. I'm sure everybody likes pizza. So let's say a pizza slice is 100 degrees, say Fahrenheit. If room temperature is 70 degrees, find the temperature of the slice at time t if after 1 hour the pizza is 80 degrees. So it's this really slow cooling piece of pizza. All right, so the first thing that I want to do is try to set up a differential equation. And I'm going to use this language to create this differential equation. So temperature decreases at a rate. So the temperature of the pizza decreases at a rate. So we're talking about dp dt. It decreases at a rate proportional to. So here's my proportion. Proportional to the difference between the temperature of the object, and the environment. So the temperature in the environment is 70. All right, so that's my differential equation. Before I continue with this, I want to point something out. So dp dt should be what in terms of its sign? Pause the video a second. So hopefully you said dp dt should be negative because the temperature of the pizza is decreasing. Well, P is bigger than 70, so that's positive. And it looks like K is, well, I don't know what K is. Is that a positive number or a negative number? Well, the truth of the matter is what's going to happen is, even though we see a K here, maybe you think visually it looks positive, what's going to happen is we're going to wind up getting a negative number here to make this negative based on this information. So what I'm trying to say is you don't need to worry about the sign of your constant. The information of the problem will fix things for you. Said another way, I just said the difference between the temperature of the object and the environment. I guess I could have also written 70 minus P. It's not really clear which one I'm subtracting from which one. Well, if I had written 70 minus P, then 70 minus P is going to be a negative number. So that if I wrote it this way, my K would have been positive. Either way, you're going to get the same answer in terms of your model. Okay, so let's check this out. Actually, once again, you guys have the tools to solve this. So give this a shot, solve this using separation of variables, and then take a look at the solution. So hopefully what you did is you first, let me do it up here. You can think of this guy as your function of t. So f of t equals k. You can think of this guy as your function of p. So we then have that, let's see, I want to put my p stuff to one side. So 1 over p minus 70 dp. I'm going to put my t stuff to the other side equals k dt. And then I want to integrate. Once again, P is bigger than 70. We're making that assumption in this model so that we don't divide by 0. That's why I wrote the horizontal asymptote there. So again, ln of P minus 70, and I don't need my absolute value there because, again, P is bigger than 70. And that equals K T plus C. All right, let's exponentiate both sides. You guys should be pros at this by now. We get P minus 70 equals e to the kt times e to the c. Or, again, e to the c is just a constant. So we get a e to the kt, and then p is going to equal this guy plus 70. Well, this problem is different than ones we've seen before because it looks like I have two different constants here. Let me rewrite this up here. So we have p, or I can write it as p of t to be a little bit more expressive, equals a e to the kt plus 70. Okay, so let's see what information we have. Well, the pizza slice is 100 degrees to start, so I guess p of 0 is 100. What else do I have? Room temperature is 70. I guess I used that in my model. After 1 hour, the pizza is 80 degrees. So I guess I know that p of 1 is 80. So I have a single equation with two unknowns, and I have two pieces of information. I bet I can solve this. So let's use the first piece of information. So p of 0 is 100. P of 0 is 100. So 100 is equal to a e to the 0. So it looks like a is 30. All right, and I also have that p of 1 is 80. So 80 is equal to 30 e to the k times 1, which is just e to the k, plus 70. Could subtract 70 from both sides, so that 10 is 30 e to the k, or 10 divided by 30, or 1/3, is e to the k. I can then solve for this by taking the natural log. The natural log of 1/3, and the natural log of e to the k is just k. So it looks like my final model is p of t equals 30 e to the ln of 1/3 times t plus 70. And I do want to point out that I said that the k should be a negative value in this case in terms of this being a decreasing temperature. And ln of 1/3, just as a reminder, ln of 1/3 is this guy down here. So here's the natural log function. Ln of 1/3 is actually a number that is negative, so I get a type of value that's expected. So those are two applications of differential equations. Both of them involved us understanding how to solve using separation of variables. And that's all I have for this lecture, so thanks so much for listening.